Okay, so let's start. I'm going to take a bit of a detour and cover one topic with this lecture 9, and before coming back to the wrapping up the machine learning part, mostly because this would be useful for the homework I'm handing out and also what Z is going to cover in tomorrow's discussion section. And this is how to get data to cloud services. So some of you have already begun to do some of this as part of your projects, but I wanted to kind of expose to you what's out there and what's kind of meant, what's the technology landscape and how could you kind of go around doing it, and specifically what I expect you to know. So in the overall picture of these IoT devices, we kind of saw, if you may, the edge tier, which is Hexaware and these kind of things, and also kind of like this middle tier, which is represented by your smartphones and home gateways, and all in our case, the Raspberry Pi, which is kind of acting as a proxy for such devices. But the final tier really is sort of what's happened out in the cloud for a variety of reasons. Firstly, that's where compute power and storage spaces, but also in many applications, you need to aggregate information from a bunch of places. And finally, just like outsourcing of computing has taken place generally, so has outsourcing of sort of services like machine learning and control and all. So a lot of products where even though you could conceivably do things at the edge, increasingly they rely on a cloud service. A great example are even things like thermostats, Google's thermostat, for example, or security cameras. A lot of these things in the past used to just rely on things at the edge and send out some sort of notification. Now they basically take a round trip through the cloud. So to cater to that, there are a whole bunch of commercial services as well as roll your own cloud service type things have emerged. If you look at kind of the way technology has developed more broadly, there are kind of the different shades of cloud services that exist independent of IoT and sensing. So one is you can rent, sort of say, a bare bone physical machine, in which case you are outsourcing the pain of having a local space, power supply, system administration, and all to someone else. So that's one. Second is you can rent a virtual machine. So there is some physical machine out there, but it's shared with others, in which case you're still managing your system and all, but hopefully you're getting a lower price point. And generally speaking, tying your capital money up into physical things is always kind of problematic. So this also kind of lets startups and all kind of do this. The third model is software as a service. So uh, instead of providing a bare bone physical machine or a bare bone virtual machine, now you begin to cater to specific verticals. And what I'm going to talk about is that. So these are services specialized for use in IoT, sensing, control, this kind of space. Just like there are services specialized for other industry segments. Okay, so the, uh, the view out here is the following, that there are sort of organizations or people with sort of deployments of IoT devices, and then the data, instead of being locally processed, gets shipped to the cloud, and it itself presents issues of uh, is it okay for you to traverse to the cloud service in terms of latency and data rates. So currently these kind of things are limited to one where data rates are low and where latency requirements are uh, doable. So for example, typically latencies to data center impact would be in tens of milliseconds, maybe hundreds of milliseconds, and which pretty much means you won't be doing your motor control loop and all around this thing, but you might be doing like motion sensor triggering a light, for example. Those things are doable. What happens out here very broadly are three types of services, so which I have kind of listed out here. So there is data collection, which is simply aggregating data, pulling in the data. Variety of different ways, and we'll touch upon some of these things, like how the transport takes place. Um, uh, Analysis. So the first generation of services didn't have much by way of analysis, but now what you see are things where you could do machine learning, you could do control, some pretty sophisticated models, and closely tied with it is also visualization. So you can browse the data, you can look at it in different ways, and oftentimes they provide sort of pretty sophisticated environments, including things like MATLAB. In fact, MathWorks, which makes MATLAB, has a service of its own like this, as does Wolfram, which makes Mathematica. So some of those standard players which were into local data analysis toolkits have kind of gotten into this. But in many cases, analysis may be very simple, like threshold, like if the sensor value exceeds 70 degrees Celsius, then send me a tweet or whatever, send me a notification. To one where you have some pretty sophisticated stuff going on. And then finally, ACT, which is again relatively less common still, but you see, so actions can range from just notifying to one where there's a command going out to some machinery. So the early player in this space was this product called IFTT. If this, then that, IFTTT or FTT, I forget. But basically it was to close the loop. The first generation stuff was really catering to non-real-time type things. Okay, like something happens, send you an email or stuff like that. But increasingly, products have gotten into more real-time notification. If you use some of these products, you would see that the delays are a fraction of a second now. So, for example, cameras on my home, when they see someone in a fraction of a second, I get a push notification on the phone. And of course, these things are also being used to control stuff. So there are plenty of examples of some pretty cool services out there. So firstly, the big players which provide general data center services have gotten into it. So Microsoft has this Azure IoT, which I know one or two groups are using. Amazon has AWS IoT, and Google actually has, Google bought this company called Lively, which was one of the very first players, and now it is part of the Google Cloud IoT. So these are certainly three of the main players in the space. And to the first order, they are very, very similar. They all provide those. I think right now I would say they provide collection and analysis, and the control part is kind of really, or action part is kind of still work in progress. Typically, when you subscribe to these, they will also happily give you edge devices which work with them. Typically, they are things like Raspberry Pi or Mbed. So those are very commonly supported by a lot of these players. Then there are a whole bunch of an IFTT, which I've already shown out there, which was one of the earlier players in the space. But there are a whole bunch of other ones which, in many ways, are actually easier to use and simpler, because to use these other services, they're meant more for enterprise scale, and also just learning how to use them in itself is complicated. But then there are other services which I think are a lot easier and yet kind of good. So, for example, ThinkSpeak started out as a kind of a mom and pop type setup, but then MathWorks bought it. MathWorks is a company between MATLAB. So their big strength is they provide MATLAB analytics. So basically, when the sensor data comes in, you can write MATLAB code, runs on the servers. There's a free account, and then for education and home usage, they have the cheap accounts, and then obviously enterprise scale stuff. So that's pretty nice. There are more products which have catered themselves to some particular niche. So, for example, freeboard.io, that focuses on visualization. So there is this concept of dashboard, where essentially you can create customized displays with cool sliders and moving needles and stuff like that. And so Freeboard specializes in that, as there are some other products. Some of them make browser-based dashboards. Some of them have apps, which you can install on your phones and tablets. Particularly useful for industrial usage or building automation and all, where kind of traditionally, there used to be whatever these control rooms with kind of lots of big displays and all. Now it kind of becomes more of a network thing. Then there are things which are focused more on programming. Node-RED, it's actually supported by IBM. This is an example of it. So it lets you program the analytics through kind of a block diagram kind of thing. So you kind of, there are lots of analysis tools, and you go to a browser window, you wire them up, sensor data coming in, action going out. All of that is kind of done. So it's a pretty nice environment. And then there are things which are more humble in their ambitions, but nice to use. So one which actually is particularly relevant to us is this MockSense. And the reason it's relevant to us is because it supports Hexaware pretty nicely. There are ready-to-use code, which actually while I'll not go over the code, but in the homework, you should be able to just use that. That's one of the options that you would have. Otherwise, it looks like ThinkSpeak. ThinkSpeak has MATLAB Analytics, which doesn't, but on the other hand, it's a lot easier to work with Hexaware because of ready codes and all. There are others like StatHat, which is if you are focused on just pushing the data and doing all sort of statistical analysis on them. It does things like 30-day forecast, stuff like that. So it has made its specialization in statistical analysis and while you're doing, I think it has some sort of a connection with Intel, if I'm not wrong, because Intel devices always supported it. But it, among other things, provides management of devices. So for enterprise usage, one of the key problems is that if you are going to have thousands and millions of these devices, how do you manage them? How do you push updates to them? How do you, all those kind of considerations which in a small scale project you will not encounter. So while you're doing kind of specializes on the deployment side of story part of it, okay, as well. And these are just some products. There are others which are kind of very closely tied to specific vendors. So like, for example, Samsung bought a company called SmartThings a few years ago. And what these guys have is all sort of sensors and actuators and all for building and home automation. And then they have a cloud service where you can write, there's a whole pretty vibrant app marketplace. So people write apps, the apps run in the cloud, sensor data comes in there. When you kind of purchase an app, if you may, that's actually hosted up there. Developers free apps, apps purchase, and so everything is kind of centralized. Kind of created a complete environment, but it's a walled gardens of sort. Even though edge devices are pretty generic edge devices, but nevertheless they have to be explicitly supported by the system out there, and you are limited to what that app provides. So this is kind of like the iPhone model, but ported to the cloud. On the nice side, though, is that you can buy platforms there which are bare bone hardware in the sense that you have a microcontroller and a radio, and you can really design your own sensor and actuator using these. So that's sort of the landscape. If you kind of step back out here, all of these services are kind of dancing around a few key concepts. So firstly, very common out here is that they will provide some sort of a API, typically a REST API, so that you can provision and configure devices. So you can tell the system this sensor is this type, stuff like that, and then also so that you can upload time series data and actually download also. So does everyone know what REST APIs are? So data transfer protocols. So there is kind of like a de facto standard which has emerged out here, besides obviously just using REST APIs and kind of bundling data as part of that. Typically, these things will also have some time series storage databases. So when it comes to storing time series data, standard database like your SQL and NoSQL database, they really don't cater very well to temporal and spatiotemporal data. So there are specialized databases which have emerged, which provide querying of spatiotemporal data. So at the heart of a lot of these systems is some sort of a visualization dashboard, ranging from sort of simplistic to some of those products I mentioned, Freeboard and all, which really have pretty sophisticated visualization. Programming for analysis and automation, again, first generation products are very simple in terms of they let you specify some rules, thresholds, things like that. But now you see complete machine learning and control apps and even open frameworks like MATLAB and R sitting behind it. Notification actions, and then finally this is particularly important, the last one for more industrial skill stuff, which is management of devices, so that you can upgrade software so that if a device disappears, you know what is happening, all those kind of things which are provided. So most of these systems have uh, all these features. Their strengths may differ somewhat, like they emphasize one or the other in that direction. Um, I actually began to use some of these things almost, I would say, this day 7-8 years ago, because the very first player in the space was Lively. It had some other name, and it was an MIT startup, and a lot of work we were doing with sensors at home and all. So we were pushing like hundreds of megabytes of data per day to these services during that. So they're pretty robust. Um, at the heart of them is the whole. So almost every service does provide a REST API thing. So REST API are built on top of the very same way that your browser clients talk to the servers. So essentially, certain words, particularly get and post actions that you can do on the data lying on there, and almost every programming language provides some libraries so that you can do it. So essentially, you access the service through a URL, and you can push data, you can send commands and get a response back. All those kind of things are provided. So the example I've cited out here is from ThinkSpeak, which is supported by MathWorks. So usually they will have APIs for reading data, writing data, and posting data. And there are certain common jargons that you would see in all of these. There is a notion of a data point, which is nothing but a measurement. There's a notion of a channel. Channel basically means a collection of data points, and then devices would be a collection of channels. So these are some standard terminology which have emerged in the space, and you would see those kind of jargon reflected in these things also. So usually, very common out here is that when you're sending or receiving data, it would be in some sort of a format, usually JSON, which is a JavaScript type language. So you kind of assemble like structure and kind of you send it out. But this could be rather verbose. Some of them also support XML, which is even more verbose. But as I'll shortly talk, there is an alternative which many of these services support, which is called MQTT. So that's another alternative, and it's designed to be kind of a lot more efficient. But this category is just basically built on top of HTML. You're essentially assembling HTML-ish type requests. So this just shows in this particular system how write data is done. So it defines all sort of formats and stuff like that. And essentially, you are manipulating and parsing text. But again, since it is standard stuff like JSON, so there are libraries that let you parse the data systematically. You can send arrays of data points. Data points have timestamps. They will provide some things like specify which time zone the data is in, so that everything is maintained in a common scenario. All those kind of things that one would expect from a service like this. And then, like I said, there are bindings. So particularly since Python is used very heavily, so there's a Python library. So one liner, it's installed in Speak, and you're good to go. And then you don't even have to deal with all that JSON formatting and stuff like that. It basically just takes care of all the stuff. So ThinkSpeak is pretty nice service, been around for a while. But I mentioned in terms of the data transport. So the other alternative, and this came out of IBM many years ago, is something called message queuing telemetry transport, or MQTT. Have any one of you encountered MQTT in your? You have. Okay. So MQTT has a much richer model. It's a lot more than simply a client talking to a server, but among other things, it describes a way of uh, formatting the data and all also, which is a lot more efficient. So it's what is called a publish subscribe model. And kind of the idea is that there is a system out there, a cloud service out there, and publishers publish data organized as topics. So it's actually a little bit like RSS feeds, which are not very much used now, but in the early days of web, they were around for a bit. But the idea is that there is some sort of a namespace where I could publish whatever UCLA slash Bolter Hall slash sensor slash. Okay, so there's some sort of hierarchical names that I can publish things under. So I can create kind of like my own channels, and then others can subscribe to it. And there is some broker, and typically in MQTT there will be a single machine as a broker, although you could imagine that there is a collection of brokers out there scattered over the world, and they keep themselves in sync, and you could talk to the nearest broker. So there is an MQTT broker, and there are all sorts of these services, and which are publishing and subscribing. And I'll talk about well, it's a standard. You need the broker, obviously. So there are commercial services which act as MQTT brokers, and there are open source things which you can run yourself as MQTT brokers. And then you have client libraries, which is what need to be embedded here, and the clients can be publishers or subscribers or both. Main thing is these things were optimized for really small port footprint. So that's one of the properties, and limited network bandwidth. So HTML is pretty verbose because it has all those tags and stuff like that. So this thing kind of is a more compact representation. And some of that you see, so this is a table I put in place. It kind of shows that HTTPS versus MQTT, kind of the number of messages that you can push through because this compactness is a lot. So what you would see is that a lot of these services like ThinkSpeak and all support MQTT as well, because there are lots of MQTT devices out there, particularly on the enterprise side, and this is a lot more efficient way of doing things. So most of those services I mentioned, they will have MQTT support. So what a typical MQTT system looks like is there is going to be a broker. One pretty good MQTT, commercial MQTT service is HiveMQ. They also have a free mode, which you can use for projects. And in the free mode, your data is all public. So when the channels you are publishing to are there for anyone to read. So whereas if you subscribe, money, private. So what you see in this case is the temperature sensor is publishing, and different clients will subscribe, and when they subscribe, whenever this guy publishes, that information is pushed to the clients. Okay, so again, MQTT system kind of takes care of that. The nice thing in the system is that it's a hierarchical topic with, and that's a very important part, with wildcards. So, for example, if you see on the top right, so this there are two types of wildcards they have. There's a plus wildcard and there is a hashed wildcard. So you can give a complete name just like a directory path, but you can also have skipped levels. So you could, for example, say I'm interested in everything which has a certain prefix, or I could say I have a path name and I don't care about what is in the middle. So there are some examples cited out here, but it basically lets you create a more general specification than would be possible otherwise. So like, for example, I can say UCLA Bolter Hall / star, so to say, and get all the sensors, subscribe to all the sensors which are in the Bolter Hall. So that's one powerful feature out here, which with the alternative approach of using this full API and all, unless they specifically provide it, if they don't, there is no such provision. And usually in those systems, you have to know the specific ID, the specific channel that you are working with. So this wildcard is a very powerful feature of MQTT systems. So what you need to use MQTT are a broker. Like I mentioned, HiveMQ is one example, but there are some other, if you just Google for MQTT broker, you'll find that there are other open source things around which you can just run on usually a Linux box. So you can just run your own. And then you need a client library. So Eclipse, that open source project, basically also has an Eclipse IO, and as part of that, they support Eclipse library called Paho, which is the MQTT client library. So super simple to use. There is this little code example out here, which if you see, it uses the Hive broker. Actually, Eclipse also runs a broker. And then basically it's just a bunch of library calls for subscribing and publishing. So pretty easy to use, and a good way for you to have a device publishing something and other devices kind of subscribing to it. What I like about these systems is they're a lot easier to use on a small scale project. On the other hand, their disadvantage is that unlike, let's say, AWS IoT and stuff like that, which provide a lot of other features and capabilities, this doesn't. But for rolling your own systems, it's a pretty good path to take. So my own, I guess, preferences, recommendations, whatever, I think ThinkSpeak and Woke are good, easy systems to do without much of a learning curve. Particularly if you're not familiar with like all those credentials and IAM roles and stuff like that, which are required in AWS and Microsoft and Google services, which just that initial barrier is pretty high. These things kind of get the job done very simply, and they all provide kind of a free mode or very low cost mode. Like for example, if you want to have your own whatever installation at home and all, then ThinkSpeak for home usage has a $90 a year mode where you can have some 30-40 devices uploading at around 20 seconds or so. Okay, so usually these different tiers differ in how often the data can be uploaded, and also support. So these two are pretty nice. WorkSense in particular, so they have a nice GitHub page, and the part I just wanted to mention is that you see out here they have Hexaware support. So what that means is that the Hexaware app on the mobile phones is actually written by these guys, and so it talks using BLE and pushes the data, and it's all open source, so you can look at how that part is working. But more also, if you go under Work Connect Python, they again have a Hexaware example out there. So essentially, you can literally kind of just use that on the Raspberry Pi along the rest of your code and push data out there. So they kind of walk you through it, and it supports all those sensors that Hexaware has. They have already got channels corresponding to it. They also have some stuff about analytics, and they have visualization, so kind of the usual things that you would expect. But you could do all of those things with ThinkSpeak also. It's just that you have to just figure things out a little bit more. ThinkSpeak is a lot more powerful. Okay, so the final stuff in this thing, which is actually, I think, frankly, a lot more fun, is to roll your own cloud service. So how do you go around doing that? So we talked in recent lectures about how you can use sklearn to run those models and all, but now what? How do you go around using those now? So kind of a very a basic idea is the following. Once you have trained this model, you want to deploy this model. So step one in this process is after you have learned, after you've gone through that Jupyter notebook type example, you serialize and save the model. So Python has this very cool capability that any data structure, you can save it into a file and then later on load it back into another instance of Python. And it will store all the necessary information. So even if it is a nested dictionary or whatnot, all of that information gets stored. So your model with all the parameters and all gets stored. There are various ways of doing it. There is something called pickle. So this is an example out here. You would see this pickle.dump, which is basically the general Python utility to which you pass any object and it saves into a file. So pickle.dump, and this is the model, and then you save it into a file. Okay, and then later on, after some time, you can do a pickle.load. So you see pickle.load out here, and after Pickle load, so this could actually be a new instance of Python in this case that is showing the same thing. So you can save it into a file, move it to your cloud service, and just run it there. Now, Pickle was designed for generic usage, and there is also something called cPickle, which is faster. So that's what I recommended. But there are a couple of other options. Specifically, if you're using sklearn, then there is joblib, which does a lot of other things, but very importantly, it's optimized for when the data structures have a lot of arrays, the NumPy arrays. And then if you're doing any deep learning type model, particularly with Facebook PyTorch, then it has something called torch.save. Both of these are built on top of Pickle, but they are kind of optimized specifically for these models. So you could, this is a joblib example, it's pretty much looks the same. So you can save. So that's step one. Step two, you now need to create a server around it. So the easiest way to do is the following, that there are lots of so-called Python web micro frameworks. And what these guys do is they essentially let you write programs which essentially act as very simple web servers. They will listen on a socket and you create your own RESTful API, and so just work with it. There are a couple which, so Flask is very widely used. My own personal favorite is SteadyPy. But basically, they very simply I think the code unfortunately is not very readable, but maybe okay. No. So this is showing the SteadyPy one. So all you say for SteadyPy, you define a class, and within the class you basically by default a method called index, which is kind of the default URL. So when you've done SteadyPy quick start hello world object, after that it basically listens on the port and it's going to respond to the standard URL like this, but you can define a whole bunch of other methods also when you can do like post. You essentially create your own RESTful API. So the idea would be that one of those methods would take the arguments being supplied, and you will run your model, which you would have loaded using Pickle.load, for example, to run the stuff. So very easy to use, super simple. You can run it on any machine. You can even run it on your local machine and create your own web servers. So, so I think it's a lot more fun to do these things on your own than to rely on these commercial services. The other advantage is that you totally can do anything that you want. You're no longer limited by the rate API limits and stuff like that. Okay, it's a lot cheaper to rent a virtual machine than to go with those services. And if you are doing it at home and stuff like that, it could just be a spare box, or it could just be while you're testing things out. Here are a few links which kind of walk you through some of the more steps in this process in terms of deploying your own models. So something worth considering. Any questions? Okay. Final thing, a few practical issues out here. So, one thing that you would see is consideration which comes up is, should your end devices be pushing data or pulling, or the data should be pulled from them? So what I mean by that is some devices will, and some cloud services are organized around the notion that the edge device calls the cloud service and deposits the data there. Others are organized around the concept that your edge device is a server, and the cloud service is going to call this guy and fetch the data. There are trade-offs between the two. Some of them have to do with availability, like for example, if the device goes to sleep and all, then obviously a model which pushes the data is superior to a model which fetches, because the cloud may be fetching. Okay. On the other hand, it's potentially easier for the cloud to fetch. You can do a lot more sophisticated things that way. One of the consideration that comes in is that lots of time devices are behind NAT. So I'm sure all of you would have used NAT for sure, So idea being that there is a single IP address and then a whole bunch of machines are hidden behind it, and that's mostly because of shortage of IP addresses. The problem with this is that or if the cloud service has to contact your device either to fetch the data or to deliver a notification or deliver a action, then how does it go out and contact the device? So what do you think would be the solution to this problem? Right? I mean, there might be a single IP address, a whole bunch of sensors sitting behind it. How do you go around solving this problem? You also face it, for example, if you have a bunch of machines at home and you want to SSH into a specific one. So how do you do it? I mean, there's at least one obvious solution, but which is have the device create a connection and keep it up, persistent connection, right? So there is persistent connection is an option. Another one which many of these NAT firewalls provide is what is called as port forwarding. So the idea is that different devices can be bound to different TCP/IP ports and then listen on those. So kind of, let's say if you have two machines at home and SSH port is a common one, 22. So maybe you can assign one machine to whatever port 10,000. So that when you SSH into it, you specify the port so that you will reach that specific machine. So almost every NAT router, your firewalls and all, will provide a port forwarding function. So you can do that. There are you also face this issue if you think about it. You again, your home machine is typically behind a NAT, and yet when people call you on Skype, they are able to reach you, right? Even though your machine does not have a public IP address. So they have to resort to some sort of a persistent connection model. When you fire up the Skype thing, there is a persistent connection which gets opened up and then it's kept up. If you are using browsers and all, there is a technology called WebSockets, which is used for this purpose. So there's a milieu of things around which help solve these problems. Another issue that we face is what about high rate data and latency critical data? So one of the challenges you would face with a lot of these services is that they put what is called as an API rate limit. That is, they will place a limit on how many API calls you are allowed to make and how many data points you can include in a single API call. So some of it has to be, you have to manage it in the sense that you will buffer the data instead of sending out single point every time. You collect some amount of data, but then you have to plan for it because depending upon the type of data, if this data is going to result in a control action, then you can't bundle up. On the other hand, if it's just some temperature data or something like that, which is not just for visualization, you don't have to. There are protocols which are specifically optimized for time critical stuff also, so real-time streaming protocols, so those often get used. Another consideration is what kind of programming environment is available out there. So ThinkSpeak has MATLAB stuff, but if you're rolling your own, that's another advantage. If you're rolling your own, then you have the full power of Python available to you. So you can really expose all sort of cool stuff around that. And what kind of automation and analysis support exists. So ThinkSpeak again has a bunch of apps and all, and again, roll your own model. You can literally link to anything that Python universe provides. So those are kind of some of the benefits that exist. So it's a lot of fun pulling up these things together. I guess there are way too many choices out there. So hopefully, kind of the list I have given to you at least represents kind of the more some of the better choices which kind of exist. Obviously, these are not the only thing out there. MQTT is standard. So that's probably the only takeaway from this thing in terms of standards, that you will encounter everywhere, and of course RESTful APIs. But all these other services, some of them will come and go, but clearly the ones from the big name players are perhaps going to be around. And anything that you roll on your own is basically all you need is some virtual machine running someplace, and you are good to go. Okay, so hopefully this gives you. There's nothing at this level. There's nothing deep about these cloud services, but there's a lot of research going on things like how do you, what does the backend look like? So now imagine in some of these services you have millions of devices sending data at very rapid rate, and you have to do all this machine learning. And also one of the research areas that a lot of people are active in is how do you do that kind of real-time big data analytics, okay, running all those models and all. At least until last year, Professor Tyson Conley, before he left, used to teach a course around that out there. So that's a big topic of optimization. Another one I talked about is time series databases, and in particular space and time, so that you can query things like you could say, what's the average temperature in a particular region in the past 1 hour, or all those kind of spatial temporal queries. So that's another area of research quite a bit. So there are sort of this overall scenario. There's a lot going under the hood in computer science research and all, but from our perspective of using these things, it's basically stitching together some of these software building blocks. And what I would say at this stage is, if you have systems with tens of devices sending data at order of hertz, that's very reasonable to do, and you can pull it off cheaply. If you, on the other hand, if you want to have much larger devices and very high rate data, then you basically have to go on your own. So just to give an example, I'm currently engaged in a project where we are collecting data from order of 1,000 human subjects. They are wearing a Hexaware type device and have a smartphone, and we are collecting raw data 24/7 because we are training models on it. So there's no inferencing, raw data. We have collected in excess of 0.5 petabytes of data. Okay, so these are like huge disk arrays and all. Okay, so you can just imagine there is no way we could even do it on at any same price point on Google and these kind of devices, and besides we lose all the flexibility. So it's all sort of custom infrastructure which is going to happen. Once we have the models, we will deploy them on AWS, because at that stage, the feature computation and all, we now know what features we need, we know what inference we need, we do it on the user's smartphone, and then we push that out. But this initial phase of knowledge discovery, kind of the data science part, there's no choice but to kind of dive deeper. Okay, so I want to switch back now to what we were covering last time, and that's the last topic that I'm going to cover, which is looking into the neural network way of processing information. So we saw previously support vector machine example. Hopefully you recall that Jupyter notebook that I walked you through. I'm now going to do the same thing, but with deep neural network. But before that, I want to give a quick, very rapid thing on what's going on. Again, without going into the underlying theories and all, but really kind of giving you a black box view of how what's happening. So what's really been happening is that for the past 6-7 years, since around 2010, a lot of sensory data, sound, images, these kind of things, as well as non-sensory data, that was being processed using very traditional machine learning methods, has suddenly been replaced by processing using neural networks. Now, neural networks themselves are not new. Kind of the basic concepts behind these go back to 40s and 50s, and there are a lot of interest on that. So this already line is kind of showing rising and falling interests. And then when I was a grad student, that was another time when there was a lot of interest and also close friends were that. And, that and then things again died down, and then with the GPUs and lots of data and mechanical turk and these kind of things, again, stars got aligned and lots of things. But some of the key things that we rely on were actually invented or discovered long, long ago. So we are kind of in this phase where neural networks suddenly have taken off quite a bit. Okay. So I've shown this picture before. The basic idea is that we think of the model, which is what we are going to train, as one where there are neurons which are organized into layers. There is an input layer. So that's what we have out here. Okay, input layer. And then the computation progresses layer to layer. So essentially, every neuron, it outputs with information, which is then received by neurons in the next layer, and which then compute their output as a function of those inputs, and that process goes on. And eventually, you get your output out here, and this output could be any number of things. It could represent, for example, like each neuron may correspond to, for example, the different activity classes we have. So one neuron will say, this is what's the probability of walking is. And the next one will say, what's the probability that the user will sleep more, and stuff like that. And then you'll probably do things like the maximum score, or it could represent something else. Maybe it represents a predicted temperature, and the other one represents a predicted humidity. So there are many different things you can do, but the basic structure is this. And the important point is, what does this neuron look like? Well, this is where bioinspiration comes in, that in biology, our brains are organized as neurons, and they get similar kind of data from other neurons, and there are lots of them. And the way information is propagated, which I'm sure you've before, is through these spikes. And the rate at which the spiking is done is says something about the value. Now, artificial neural networks do not operate with rates, although they're somewhat towards that also. They operate purely in terms of numeric values. So what we have is kind of a system where a voltage or a set of bits represent the output from neurons, and it feeds into a neuron, and then we have the output. And a very common model is that we take a linear sum of the weights. So that's this part, where theta is matrix, and then we apply some sort of what is called as an activation function or non-linearity. So this G is the activation function. Now bear in mind that if G itself was linear, then all that multiple layers basically reduce to a linear function. So that would not be very useful. So, but if G is a sufficiently rich nonlinear function, then you can show that the kind of system we have out here, this one can compute anything. In fact, just 2 layers are enough to compute anything given sufficient number of neurons. Okay, so I've shown this slide before also, but very commonly sigmoid and hyperbolic tangent are some of the non-linearities used, but another one which is used a lot is called ReLU. And so it's like sigmoid and hyperbolic tangent, except that it rectifies the negative side. And it turns out that it works pretty well and is some nice. At the end of the day, what's really happening is that in a typical classification job, the outputs that we have out there, they represent probabilities. So they say probability that output is y given x. That's what they are spitting out. Okay? And we are going to take the max of them and say that's the winning class. Okay, so then the job of this model boils down to, like any other machine learning task, what are the parameters? Right, so in case of SVM, the parameters were for those hyperplanes. Here, the parameters are all those weights. So the approach, again, which it uses, pretty much the same as in those machine learning other things, which is you guess the initial parameter, you calculate the error, you calculate the error, namely this is the cost. So how far apart am I from the ground truth? Calculate the derivative of the error and then change the parameters. So we calculate the derivative and then move in the right direction. So, or in particular, we calculate the gradient and then we move. So if I'm thinking of this is an error, so we want to minimize the error, so we are going to move negative of the gradient. So that's all that goes on in learning. The challenge though is that within all of these, there are two issues. One is how do I calculate this derivative? Particularly, derivative of a single neuron is okay. If you have this deep network of neurons, how do I calculate derivatives? And I have tons of parameters. And the other thing is change the parameter. What strategy? Okay. So calculate the derivative. The question there is how, and change the parameter. What algorithm? Right. What should be my strategy? So for calculating the derivative, another one is what is my error? Okay, so here I have picked as an example just least square error, but actually there are better error functions to use which are informed by information theory. Okay, so, but we'll have some error function, and the idea then is I want to calculate what is the derivative of the error with respect to the parameter. And this is where you make use of chain rule. So the simple version of chain rule we would have always seen, which is if let's see, if y is f of x, then dy over dx is sorry, so I want to calculate dy of d theta. Okay, so actually let's take it back. So I have an error function, and let's call this output z. Okay, so error is calculated from z. So error is a function of z. So de over d theta is what we are after. So we are going to calculate de over dz times dz over d theta. So it's always the derivative of the error with respect to some parameter that we are after. Now, what happens in this particular case is that that I may have to look at I have many different sort of variables that I have to worry about. So in particular, I'm looking at parameter theta I, which corresponds to whatever is multiplying this guy. So you may have to do summation over multiple things. So what's referring to the following, that if I have a variable out here and my error of interest, if there are many different pathways through it, then I'm going to apply chain rule on each pathway and then sum them up. So that's what we end up looking at. Okay, so it's very mechanical, but one has to just keep tie on it. And then if I have a deeper network, then I have to propagate back. So at every step, I would have some parameters in the output layer, some parameters in the middle layer, some parameters in the input layer. We kind of go back. So at every step, what we do is we calculate. We start out by derivative of error with respect to itself. So that's one. And then we kind of go back and we say, what's the derivative of error with respect to parameters in this layer? And simultaneously, we also calculate the derivative at each step. So let's take an example out here. So this is my output, yk. And my error is e. So I'm interested in finding out the derivative of e at every step with respect to some parameter. So at every step, what I do is I look at I compute. I'm going to compute a series of these things. So as I go backward, I say what is the derivative of e with respect to one of these variables, and then the e of theta So at every step of the way, I'm going to calculate error with the parameters in that layer by looking at the error derivative of the error with respect to the output of that layer, which I'm going to keep computing, and then what is dz over d theta, which is just a function of this. So I'm going to keep going backwards, keeping track of derivative of a variable in between the layer, derivative of error with respect to those variables, and multiplying it by the derivative of the variable with respect to the parameters. And then simultaneously, I also compute the derivative of the error with respect to the next set of variables. So this kind of it's a lot of calculus bookkeeping. Main thing is it's actually super simple to do for an algorithm. So all these deep learning networks, one of the key things that they provide is that once you give them a network, they can automatically calculate all those derivatives for you. So while in a proper formal course, they will force you to kind of go through all these derivative computation, but tools do it for you, and essentially you compute what is a forward pass where you compute all the values, and then you go back and compute all the derivatives, and that's why it's called backpropagation. So discovered back in 80s, pretty routine, and this is called auto grad functionality. So you will find it in tools like TensorFlow, PyTorch, all these tools. Their main claim to fame is that they compute these derivatives automatically for you. And once you have the derivatives, then step 3 is solved. That is, at all points, I can always compute the derivative of error with respect to any one of those parameters. So the tools do it for you. And then the second part is, given that derivative, how do I update the parameters? So intuitively, the idea is that if I'm moving away from the goal, then perhaps I should adjust the weight towards the goal. So there are intuitive strategies again for this purpose. So you can visualize this thing as my goal is to get to the valley, and therefore at every step of the way, I'm going to find the pathway which is one which is going downhill, and I'm going to take a step in that direction. So it's the mathematical equivalent of that called gradient descent, which happens, and that's kind of a basic algorithm that after we calculate all the derivatives, so this is the backprop step. Finally, we update theta by multiplying it with something which includes the derivative. So in this case, what we are seeing is theta is being updated as some proportion of the slope. And a lot of work has gone on variants of this equation, because it turns out the simple strategy of just taking a step doesn't quite work. You want to take into account of what did you do in the previous steps, and also all sort of algorithms. They're all kind of heuristics, but the basic structure is this. Again, to be able to use these systems, you need superficial familiarity with the concept, but other than that, they're kind of like black box. Think of it this way: there are zillions and zillions of people working in this space. Very few actually know what's going on under the hood, because you don't need to. They're kind of using these systems as black boxes, and for all practical purposes, that suffices. So you can pick up a learning script from someplace, which kind of implements, basically these tools take care of almost everything for you. The problems that you face are, in the state, too many parameters, and the second problem that I'll talk about shortly. But to deal with too many parameters, I have all these layers, and each neuron is connected to every neuron in the next layer. There are too many parameters are big, your model is big. So your model is big can be a problem because if you're trying to embed it into a tiny little device. Okay? So there are a variety of different ways you could go around doing it, but the very first thing is you reduce the number of models. Reduce the number of parameters. The second thing you can do is you can reduce the resolution of the parameters. Like instead of having floating point, maybe you can have int, or maybe you can have even 1-bit bits. So people have tried all those things. To reduce the number of models, there are two properties that we make use of. One is what I call a structural locality, which basically refers to the fact that the output at any given point in space does not depend upon faraway things, not to the distant past and not to things which are far away in space. So at any given point in time, if it's sensor data, then the output will depend upon those neurons which were receiving nearby values in time or nearby values in space. So instead of computing something based upon the entire time series or the entire image, we can just focus on a tiny little part. So, and moreover, the other thing, in this case from imaging neuron, which is translation equivariance. So equivariance refers to the fact that if I shift the input, then the output shifts. So let's say you are trying to detect a peak. If in the raw sensor data, so let's say my original waveform looked like this, and the output was, actually this is a bad example. Let's say there's some waveform. Okay, I'm pretty awful at drawing, but and let's say I was looking for things dropping below this threshold. So I'll get an event at this point. Now let's imagine I shift this whole waveform. Then the location of that event will shift by the same amount. So equivariance refers to the fact that when I shift things, then the output also shifts by the same amount. What that means is that if I had a neuron observing this time, a neuron observing the time here, and a neuron observing this part of the time series, and a neuron observing this part of the time series, if I look at a window and of time and divided it into slots, and I had a neuron observing these different slots in a window, then all those neurons should behave the same, because if they are trying to detect a peak, because if the peak were to occur in slot 1, and this neuron will do the same thing as the neuron will occur if the peak were to occur in slot 5. So what that means is that firstly, neurons are looking locally, and second thing is all neurons are the same. If all neurons are the same, that means they can have the same weight. So we basically share the weights, and we keep each neuron's receptive field, as they call it, what it depends upon, small. And these two concepts come into play into the way we process information, and we reduce the number of parameters. So instead of taking the whole input and then having each neuron feed to every output, as might be the case over here, I have an input vector. Let's say I have an image 32 by 3, so I can think of it as 3072 numbers. Instead of every number affecting each one of these 10 outputs, I can go back to the fact that I really have an image, and that I'm going to organize I'm going to think of it as if I have a little pattern method, and I'm going to look for patterns in different parts of the universe. And it's a single pattern method. It might be a pattern method like my peak vector. So I'm going to slide this thing around to different parts of the image, and at each location it will feed to one of the outputs. So essentially from an input image, I get to an output image. So I maintain this spatial structure, or in case of time, I maintain time, as opposed to having, so a pixel out here, for example, this guy will only depend upon this part of the image. A pixel out here will only depend upon this part of the image. And moreover, the way it depends is exactly the same. It's the same set of waves, it's the same pattern. And you can think of it in space, you can think of it in time. So now what has happened is that instead of those large number of things, 10 times 3072 weights, I only have 5 times 5 times 3 weights. Okay, so a lot fewer parameters are being used up there. So, and then I can have multiple pattern measures, either in space or in case of time, multiple pattern measures for time. So my initial image gives rise to a bunch of images, or my initial time series is going to give rise to a bunch of time series. This is basically features. Each stage, I'm computing some features over it. So if I had a time series, every window, I compute a feature over it. And that feature corresponds to, in our case, the feature happens to be this weighted sound activation function. So every time window, I compute a feature. Every time window, I compute the same feature again. It's just with the different values. That's what happens in this approach. And then what we do is we take a series of these things. So we start with our input data, we calculate features, so I get a new time series or a new image, and then again I calculate features, again I get a new time series or a new image, and so on. I keep that process going. So what ends up happening is I may start out with an image of a dog or a time series of some data, and then through a series of refinements, I get another image or another time series, and then another image or another time series, and I keep going through these steps. And then finally, what I would have is features which are higher. So for example, my initial things may recognize edges and all, or they may recognize peaks or frequency components. And then I stitch them together to more complicated patterns, and then more complicated patterns. So it's like a looking at my data with kind of pattern matchers, and then I step back and I look at that time series of features with another pattern matcher, and then I step back and I look at it with another pattern matcher. So all of this concept is something which has turned out to be pretty powerful. The nice thing here is you don't have to figure out what features. When the weights are learned, then the system automatically figures out what are the good features. In this example, after the network was trained, in the first layer, the pattern matchers look like this. And you would see that it learned how to, like, for example, vertical edge, horizontal edge, and diagonal edges, and stuff like that. So it automatically learns interesting features. And in some of these things, you would see that by the time you hit the final layers, you would begin to see that there are features corresponding to faces or nose or lips or stuff like that. And there is biological analogy to this. So I once heard a talk by one of the neurosurgeons at UCLA, and these guys did these experiments where patients with certain kind of brain disease and all, they kind of put electrodes and they showed them video and music and all. And there are things like there are neurons which are so specific that, like you were showing that when Bart Simpson's face would come up on a video, then that neuron will trigger. Or when a particular, right? So the neurons get tuned to very specific features which are perhaps of importance in life. Same thing happens out here. That after all of this training, the system begins to recognize important features. To give you an example, and this is kind of how these things can go awry. So I read about a system where it was trying to recognize horses against other animals. So there were cows and dogs and all, and there were horses. Okay, and the system was doing pretty well. And then they looked at what were the feature causing the horse to be detected. And it turned out that in that training data set, all images of horses had a particular logo on the bottom right. And the system learned to recognize that, nothing else about the horse. It just learned to recognize the existence of that logo. So you have to be careful that it could be any feature. But anyway, so that's what happens out here. Second problem, which is, so that's convolutional neural network. The second thing is there is no memory in the system. So at any given point in time, that network takes a set of input, makes a decision, then I offer the next input, it makes the next decision, and there is no memory carried over. And sensor data is not like that. Sensor data is a time series. Now, you could still use CNNs pretty successfully. So there is a lot of work like what they do is essentially the two broad approaches. One is I can convert sensor data to an image, and then I can use neural networks for image recognition that exist, and there are excellent ones out there which you can just download and use. So, for example, if I give you this sensor time series, which is shown out there, I can calculate a spectrogram. And we as humans often, by looking at spectrogram, are pretty good at recognizing things. You can think of this thing as an image, and you can basically run an image classifier. In fact, that's how human experts operate a lot of time. Or, for example, I may give you motion trace of an animal or a human, and then by looking at this, you can maybe make predictions about things. Like, for example, Brett Papers were looking at animal mobility trace. They can tell how old is the animal or what the gender of the animal is, and I suspect the same thing holds true about humans also. So I can think of it as just an image and look at some characteristics. So that's one way I can apply. I think the other one is I can, instead of working with images, I can think of kernels which are one-dimensional kernels. So I can apply the same concept of pattern measures to the convolutional neural networks, but now to the time series. So all of that can be done directly, but still no memory. We still fundamentally face the problem that the decisions are being made independent in every window. So what that leads to is a concept called recurrent neural network, which is essentially like combinational logic is to finite state machines. It's the same thing. Convolutional neural network to RNN is combinational logic to sequential systems. So what we want is the following. Instead of conventional thing, this is like a combinational logic. I give you an input, you produce an output. I give you a new input, you produce a new output independently. To one where there are some concept of a sequence, some memory. And there are a bunch of different scenarios that occur. So one example, maybe I can give you an image, single input, and I want you to give me a caption. So caption is a sequence. So in that case, the system is generating a sequence of words. Or I can give you a video and I can say label it. Did it represent cooking or sleeping or whatnot? So you can look at the whole sequence of input and then produce the one label. So this is one to many, this is many to one. I can have many to many. I can speak a sentence in English and you translate that into German. So that would be an example of a sequence in, sequence out. And then finally, I could have a situation where I'm giving you frames of video or windows of some sensor data, and then you are trying to make a prediction in every window or every frame, and your prediction are going to make use of the history. So they're not independent predictions. You are going to keep looking what happened in the past. Also, this is a point we saw in hidden Markov model also, which is there is if you observe something, then something about the past does matter, and that's what is happening here. So to capture this notion, there's a type of neural networks where what we do is we create a feedback. So instead of X resulting in Y, there is also a hidden state. It maintains some memory. So this is the hidden state, H. And we update that also. So the hidden state at time t is some function, again using those neurons, of the hidden state in the previous step and the current step. So we keep this, if you have done a digital logic course, this is like the register in your finite state machine. That you keep a value, and the next time again you use that value and you update it. So you're outputting something and you're updating the state. So that's the concept in recurrent neural network. In time, it looks like this. I'll have some starting out hidden value x0, and I'll get the input x1, and I'll feed it into this neural network, and I will get h1, and I'll also get y1. Okay? And then I keep repeating this process. But every step I'm using the same weight w. So it's the same function fw, which is being applied one after another, and now my goal in this case is to learn this fw. Just like previously we learned the w in the standard neural network, now I need to learn all those parameters. And now what we do is, to train these things, we just adapt that old algorithm. Again, tools take care of it, so we never have to do it manually. I'll give it a sequence, and it's going to produce a sequence, and I'm given a sequence of labels. And I'm going to compute the error, I'm going to compare the error, and I'm going to compute the loss. And then I'm going to update those weights. Except I have to not do it across time, because the value here is depends upon everything in the past. But you can't keep track of past forever. So usually what we've done is, always what we've done is to look at a time window. So I'm going to look at all the samples in the window and update the weights. And I keep repeating this process. So this is, so at every window I update the weights based upon what the error was in that window. And I keep doing that process. And there are a few what goes inside these boxes, what the kind of function is. There are a couple of very commonly used functions, something called long short-term memory and built-in recurrent things. These people have figured out work very well. So this is called LSTM, short form, and this is called GRU. So they are very commonly used. They're provided by these frameworks. So you create a network, you say this has an LSTM unit in it, and then it trains it. It takes care of finding the gradients over time and all, and you are kind of done with it. Okay, so what this leads to is the following. If I'm looking at sensing, I can start with my standard fully connected neural network. I can reduce the model size by going to convolutional neural networks, and I can add time by going to recurrent neural network, let's say LSTM. And then, as you might imagine, I can combine the two. So there is convolutional networks which are made. So that's the landscape of things. So for sensor data, this is probably where the most useful type of models are going to lie. Video will be the same way, speech is going to be the same way. On the other hand, if you're looking at static images, or if you're trying to do a single window of sensor data, then it will probably be this guy. MLP you will probably not use because it's way too many parameters. So single window here, and sequence for this one. The sequence you will either do this or this, and single window. So let me show how this works out. And okay, so yeah, okay. So I'm going to show you on a couple of examples. Again, our good old human activity recognition. So previously what we did was we had sensor data, we divided it into windows, and we calculated features over those, right? And in our case, the data set already gave us the features, and we focused on which features are. So standard approach, sliding window, feature engineering. So we spent a lot of, we had this whole approach of letting the system find which one of those 560 plus features were the good ones. And then we learned the weights and did the pattern classification. Instead of using that, so trying to find the features, which features and all, what we can now do is to work straight away with raw data. That becomes a possibility because those pattern matchers in the input layer are nothing but my feature detectors. So let the system learn about it. But if you wished, you could still use features. You can still manually linear if you want it, but you can also go. So let me show notebook to see how this kind of code looks like. And again, you are welcome. I'll post it on Piazza. You are welcome to use it. Okay. So what we have here is human activity recognition using LSTM. Now in this particular case, I'm using a different data set, which is again from that UC Irvine this one is called PAMAP2 physical activity monitoring data set. And in this particular case, a bunch of physical activities were performed, some HMUs and heart rate monitor and stuff like that, kind of like what we have in our Pixel. And which type of protocol they use and stuff like that. And actually, the version of data set we're using doesn't have 18 or 12 physical activities, but the point is the same. So IMUs, heart rate monitor, and this is raw sample data. So what this notebook does is, first thing, we load the data. Now in this case, the data is in the MATLAB format. So it turns out in SciPy, there is a load mat function, so it just loads MATLAB data. Okay. Then this data set has training, validation, and testing, 3 types of functions. So if you recall, there was training and validation is what you should use at learning time, and then testing you should set aside and then touch only after the model is fully trained. In this notebook, there's enough work, but testing and validation is fine. And then this particular notebook can work with any type of 4 networks, fully connected one, LSTM, a convolution LSTM, and a CM. So it provides support for all 4 type of neural networks. Then the hard part out here is defining your neural network. How many layers you should have, how many neurons you should have in them, and these are all a little bit magical in the sense that you have to decide. These are what are called as hyperparameters of the model based upon scene, you play around with it, but you could use, this is something that I picked up from a tutorial at a conference, so this is kind of a reasonable starting point because the type of data set that you have is similar. So now, creating, so remember I told you that the tools already take care of the calculating the gradients and all, but you still have to specify the network, and specifying the network neuron at a time can be super painful. So what happens out here is there are 2 packages being used out here. The underlying package is something called TensorFlow, and TensorFlow is a toolkit from Google, but that still is painful to use for people. So what another package on top of it is called Keras. Keras lets you specify a neural network very easily, and then at the back end it just uses TensorFlow. So what you see out here is I imported Keras, and then out here it says using TensorFlow backend. So it automatically, a couple of backends it supports. In this case, it's supporting TensorFlow backend. And then when I'm specifying my neural network, I can simply talk in terms of, let's see if we could zoom in. Yeah, so see out here how I can simply say add an LSTM layer of size 32, or add a convolutional, 2-dimensional convolutional layer, because this example is for images. Sorry, this example is for, it works with multiple time series to add a convolution 2D, and you have to specify how many inputs, what the kernel size is, and it takes care of kind of generating and wiring up all those neurons. So this part basically goes into in sequence adding the layers one after another, and there are some details out here which again only a more advanced course will teach you, but you see that if depending upon the network type being convolutional STM or CNN, or it kind of does different kind of things, but at the end of the day what we have is kind of the structure defined. And once I have the structure defined, then after that the job is pretty simple. So we declare a module depending upon what type of thing what we are doing, and then finally, so we create the summary of the model, it builds the model for us, and then we do the training. And for training, we end up using sklearnback, and then it produces a result. In this particular case, what you see is it gets an F1 score. F1 score is something which is combines accuracy and false results, and 0.66. Not too great, but on the other hand, we trained it only for very little time. So if I go back out here, it only trained for 3 steps. So in that loop where we adjust the weights, we trained it only twice. And you see that the accuracy on validation set, it was 73%, but the F score was 66. So if you have sensor data and you want to kind of work with this, you can adapt a model like this very easily and kind of use that as a classification tool. The advantage here is, like I said, you're not playing with any features and all. You're directly working with the sensor data. The disadvantage is that you'll probably have to train for more steps, and you will probably need a faster machine to work with this thing. But it's a pretty viable thing to use at this stage. And again, the trick is not to start from scratch. If you're working with images, these toolkits give you good classifiers which are already trained by Google and Facebook, respectively. So you can just blindly use those. But if you're working with other types of data, as you would be, then working with things like these would be kind of a good starting point, and then play with it. Or kind of working with like data. This is still something you would do only if you are deploying your model on a Raspberry Pi or on a cloud service. If you are doing it on Hexaware, this is still quite painful. One advantage of things like Knifebase is that you know what the features are. So you can manually compute them on Hexaware side and reduce them. And here, you could do it by looking at the weights. One of the problems that you face is that the weights are all floating point numbers. So your Hexaware would be doing a lot of floating point computation. On the other hand, it does have a floating point unit, so it's a viable solution stuff. So this is a very so again I'll sort of post both these notebooks in case you wish to use them. Again, my recommendation, Knifebase, because that's the easiest, simplest thing to understand. But if you want to attempt any one of these, don't do from scratch. Use the SVM notebook and neural network notebook are both that you could work with. What LSTM does give you is that you can look at the sequence and therefore hopefully get better results than simply doing it window at a time. So anyway, that's what we have here. And the final thing I want to give you is another example. And I'll not walk through it, but I'll give the code for it. So this is hot word detection or keyword detection. So this is like when you say to these devices, "Hey Siri," or Alexa or Google now, those kind of hot phrases or hot words. So this example kind of caters to those kind of applications where using speech or sound as your sensory input. So the standard approach when working with acoustic signals is again hand and linear features and using GNMs, which we talked about last time, and then we use HMM to smooth the approach to kind of take care of this thing. The neural network approach to this thing basically deploys raw sound signals and directly feeds them to a horizontal neural networks for different things like what kind of scene is it, like if there's a lot of sound in a restaurant or a home, emotion different, stress different, who's the speaker, all these kind of things. So the example code that I'll post again from these guys, it's a system called DPeer, does that. And main thing I wanted to point out is that over a classical technique, that is a zero color thing, you see that the neural network is much better by huge margins. So on some of these things, even for these toy examples, you begin to see that the neural networks perform much better than sort of feature engineering and those kind of approaches. So in this case, DMMs do pretty well for background noise level-based ambient scene analysis. They kind of do okay with stress, but you could see that the DMM is doing better. But here, particularly on this one, speaker identification DMM does quite well. So something to keep in mind, and I think even if you don't end up using in your course project, I mean, in future when you encounter sensory data, bear in mind basically that this is another pretty powerful tool which has emerged, which kind of lets you do sensor processing in a very different manner than otherwise, but it's still a growing technology. We still don't have things which you can easily deploy on embedded devices, but even those things are rapidly emerging. Some ARM, for example, which makes those processors, they have a group on machine learning now, and they are actively working on providing libraries for doing deep neural networks on Cortex, those kind of processors. So in a year or two, we'll probably have good robust libraries to be able to work with this thing. Not today. Okay. So that's what we have. So I'm going to stop out here in terms of the main material of the course. So next week, the plan is that we are just going to spend time on reviewing. Tuesday, Amr is going to conduct a review, and Thursday, I will conduct a review. Okay. Lot of the material I presented, that was more of a black box view. So obviously, I don't expect you to know how to do backprop or those kind of things. Okay, I mean, these are just FYI. I mean, the perspective is that hopefully you get to use them at some opportune time, and maybe even if you never take a course on neural networks and all ever, at least you have some familiarity, because a lot you can do with the kind of tools out there combined with some amount of self-reading. The type of material I do expect you to know is the one where I went into depth under the hood. Okay, so I'm referring to kind of the exam on Friday. So again, we'll do 2 reviews, and I'm going to be the homework that I'm sending out is basically going to ask you to take the sensor data and publish it on one of the cloud services of your choice, but preferably ThinkSpeak or WorkSense. And the other one is I want you to show identical time on 2 Elsevier. So this one you have to do in pairs. Okay, so no, not individual. You do 2 people together. It could be your project partner. If you don't have a project partner, then team up with others. But 2 people. We have 18 students in the class, so it's even number of students, and so those will be the 2 things. Okay, and let's see. So I'll see you guys on Tuesday. I'll see you guys tomorrow. So tomorrow, what G is going to do is he's going to walk you through how to do the heart rate sensor, which I know your group is dealing with, and I think some potentially other groups as well. So it will give you another example, and I'll post all these code in the homework. I think between what Z has already posted and the links that I'm providing for WorkSense, you should be able to pull that part off by just sort of stitching those pieces of code together. It should. Okay. So, any questions? I'll have my office hours, and I know some of you are struggling with Windows 10 issues, so come and see me. I'll try to help. When the homework will be due? You can take your time as long as you submit it by middle of the finals week. Okay. The day of the day of the last day of the quarter, yeah, the finals day, right? You basically before you show up for the thing, all the project material should be in. For the homework, I'll probably set the date middle of the finals week, so that we have a little bit of time to grade that one. The only thing which will be after the time slot would be the peer review that you have to do. Okay. Yeah. We are doing it actively. Hopefully, we'll have it some of it by tomorrow, and then the code part is still a little time. But yeah. Any other questions? Okay, so hopefully, I mean, again, I went over a lot of this material, and I know, look, I mean, the entire course is on neural network, and I kind of took 1 hour, okay, but what is covered in maybe 10 12 lectures is obviously in a lot more depth out there. But this was more of a functional view, and I'll post both the code base, and you can kind of think of it as more of a black box thing. And if you seek to apply it, come and talk to me, and I can guide you through it more closely. But then don't do it unnecessarily. But if you are seeing, like, for example, the quality that you are getting from the other analysis is not very good and all, then consider these other options. Come and talk to me. Maybe I can kind of guide you on some of those. But I think many of you on your own are kind of reading papers and all to figure out good algorithms, and that's terrific. But in any case, so that's the kind of stuff, by the way, which I presented. I mean, the stuff has appeared in the past year or two. So this is pretty cutting edge usage of these kind of technologies. So, and a lot of this stuff is presented in a much more utilitarian fashion. It works. No one knows how and why. Okay. Sorry, there was no break today. I forgot, but. So I'll see you guys tomorrow in the discussion section. I will not present. He's not present, but I'll be there. Oh, also, let's see. So next Tuesday, so next Tuesday only Amr will present. If by any chance there is again some medical issue on his front, then we will cancel the class in that case. Okay, I will let you know, but hopefully that will not be the case. He seems to be back, and so we'll do the review. I will do the review on